my name is Nako Nakatsuka. I'm a fourth year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. So now we move on to the very important topic of stereochemistry, and consider this just an introduction because this is a very big topic. But to start off, stereochemistry is a chemistry that studies the properties of stereoisomers. And at this point, you probably don't know what stereoisomers are, but they're basically isomers that have the same formula and the same connectivity of the atoms, but they differ in the position of atoms in space. And so now let's check out this diagram that I pulled up for you right here. The first pair is of CH2BrCl. So we have one carbon, two hydrogens, one bromine, and one chlorine arranged like so. So when you look at it, they have the same molecular formula. They have the same atom connectivity where there's a central carbon with the four other things attached to it in this tetrahedral structure, and they're also superposable. So what they mean by superposable is that by just rotating some of these bonds around the central carbon, you can rearrange it to look like this. And in this case, we have two of the same atoms, and that's going to be very important. And so the first pair is identical. They're the same exact compound. Also, I really recommend that you make these molecular structures yourself using those molecular structure building kits that they provide for organic chemistry students. And those are really helpful for you to actually visualize that something is superposable, where you can actually rearrange it by rotating around the single bonds to create the same atom. On the other hand, now let's check out the second pair. In this case, we have the molecular formula CHFBrCl with a central carbon atom bound to four different atoms. Now we have hydrogen, fluorine, bromine, and chlorine. So again, we have the same atom connectivity where we have this tetrahedral structure with the central carbon attached to four other atoms, but now it's non-superposable. The reason for that being, however much you rotate it, you can't get over the fact that the hydrogen, bromine, and chlorine are in this order right here, and over here it's bromine, hydrogen, and chlorine. So when you make these two separate molecules using your molecular kit, you'll find that however much you rotate any of the bonds, you're not going to be able to create two of the same structures. And that's, I'll talk about it later, is because these are stereoisomers, and they're non-superposable because they have a chiral center. But we'll get to that in a second. So here's an introduction to stereoisomers. They're two different compounds where the atoms differ in the position in space. At this point, I wanted to show you this very, very useful flowchart because you're going to come across a lot of different forms of isomerism, such as constitutional isomers, conformational isomers, stereoisomers, and you might get a little confused. So this is a really good flowchart to refer back to, where whenever you see a particular molecule or a compound, you can be like, okay, let me follow this flowchart to figure out what kind of isomerism I'm seeing. Okay, so let me walk you through it. Do the compounds have the same molecular formula? No, then they're not isomers and you can dump it out. Yes, then you have isomers. Do the compounds have the same connectivity? And if it's no, you have constitutional isomers. So constitutional isomers are isomers that differ in the sequence of the atom connectivity. So they have the same molecular formula, but they have difference in sequence of atom connectivity. And if they do, yes, have the same connectivity, then we move on to stereoisomers, which is what I just talked about, where they have the same formula and connectivity. So now we move on to, can the compounds be interconverted by rotation about single bonds? And if you have yes, now you have conformational isomers. And conformational isomers have the same sequence connectivity but can be interconverted by rotation around single bonds, just like it's saying right here. So if you remember, looking at the Newman structures that I mentioned very briefly before, if you have a structure that is eclipsed, this is staggered, versus eclipsed, which I'm going to draw now, where this chlorine is going to be here now, hydrogen, hydrogen. Whereas you can see, these two are conformational isomers because I just rotated the back carbon around this axis in order to go from staggered to eclipsed. And remember, staggered has a lower energy and it's more stable than eclipsed because of the steric hindrance between atoms in the case of the eclipsed. But anyway, let's get back on track. If the compound cannot be interconverted by rotation around single bonds, then we have configurational isomers. And within the configurational isomers, we have a couple of things that we're going to talk about in greater detail later on. So configurational, let's keep going, is the isomerism at a double bond. Yes, then it's a geometric isomer. And you can see here that we have trans and cis isomers, where cis is when the two big groups are on the same side when you cut the double bond in half, and in the case of trans, it's when the two big groups are on opposite sides when you cut the double bond in half. But now moving on to if the isomerism is not at a double bond, then you have optical isomers. And optical isomers are something I'm going to cover later on in this topic, and they're very important when talking about stereoisomers. So optical isomers are the compound's non-superimposable mirror images. If it's yes, you get enantiomers, and if you get no, you get diastereomers. But these two guys I'm going to talk about in greater detail later on, so I won't get into it too much. But I think this flowchart is really important for you guys to understand because there's a lot of problems in this organic chemistry topic where you're asked to figure out whether you're seeing constitutional, conformational, geometric, or configurational isomerism. And this is a very good way for you to just figure out which one it is. So I wanted to talk about a couple of historical perspectives before getting into more of the stereochemistry, because knowing about where stuff came from is actually really advantageous when trying to understand the conceptual stuff behind stereochemistry. So the first topic I'm going to cover in terms of the historical perspective is light. So first off, let's talk about this guy, Christian Huygens. Not sure how to pronounce that. But anyway, in 1678, this guy discovered plane polarized light. And what plane polarized light is light is made up of vibrations that are electromagnetic, and some materials have the ability to screen out all the vibrations apart from those in one plane. And this is what's called plane polarized light. So, as an example that I like to give, if you have Polaroid sunglasses, right? If you wear one pair on your face and hold another pair right in front of you, no light actually gets through and you see darkness. And that's because the polarides are crossed, and basically it's blocking the plane polarized light from one with another. So this guy figured out plane polarized light, which is really important when we talk about stereoisomers. And then Jean-Baptiste Biot actually found out that some natural substances also rotate plane polarized light. So if you look at this diagram, you have plane polarized light where it's just in one direction instead of all the 360 degrees. And then when you put it in a tube containing a liquid organic compound or solution, when it comes out, the plane polarized light rotated, or it changed the direction. And so this was really important because he found that optically active substances rotate plane polarized light, which I'm going to start abbreviating as PPL because that's a lot for me to write every time, and optically inactive substances does not rotate plane polarized light. So this was a way to actually characterize whether some material was optically active or inactive by performing this experiment where you can see whether the plane polarized light was able to get rotated by a certain angle. So from here, we come up with these two definitions: dextro-rotatory, which means that something rotates plane polarized light in a clockwise direction. So like so. And then we have levorotatory, there we go, which is when it rotates plane polarized light in a counterclockwise direction, like so. And this was extremely important because later on we'll talk about enantiomers and diastereomers, where, as I mentioned before in the flowchart, these are optically active isomers. And you're basically going to get different chemical properties or physical properties based upon the fact that something can rotate light in one direction or the other.